Inau- Good morning, everyone. Our inauguration session will start shortly after 10 minutes. Kindly wait to join our dignitaries.
Hello, Ramji. Hello. Hello.
Ji, sir.
Yeah, am I audible?
Yes, sir, you are audible.
Yeah, okay, okay. Go ahead. Go ahead.
Good morning, Ramji.
Good morning, sir.
So my voice is audible.
Yes, sir. Your voice is audible.
How sir? Good morning.
Yeah, good morning, sir.
Seems to be
Sir,
Yeah.
like
sir,
we are doing
you
fire,
are
fire,
you are
fire.
live telecasting, sir. You
Oh,
are
okay.
you are in YouTube right now.
Okay. See.
No, this is a testing kind of stuff. So
Yeah,
no.
testing.
Yeah, testing
Like
whether I mean
hello 1 2 3 like that.
yeah.
Under testing, huh?
Yeah.
Ram. Very good morning, Ram. Good morning, Ram.
Good morning, Vishnu sir.
Arey, Rahul sir, good morning. Audible,
Good
na?
morning. Audible. You are very much audible.
Thank you, thank you. Huh?
Yeah, we have already done the testing. I mean, yeah.
Right. Huh? Thank you, thank you. Huh?
Yeah, we have already done the testing. I mean, yeah.
Right. Arey, very good team. Huh? Ashraf, Chandrajit, Ganesh, how busy? Huh? Very good.
Good morning, sir. HOD sir, good morning.
Good morning.
Good morning, sir.
Hi, good morning, Govinda. Huh?
Good morning, sir.
Good morning, Vaishnav sir.
Hi, good
Pal
morning.
madam,
Hey,
Pal
good.
madam.
All communication people join, na? Very good. Huh?
Yes, sir.
This is
Pal
spirit.
madam.
Really. Huh?
I think our Pal madam is also joined.
Where is Paul
Madam.
Madam? We could not see Paul Madam. Huh?
Pal madam is there.
Good morning,
I
Madam.
think her network is having problem.
Mobile network especially. Good morning, sir.
Ji, sir. Okay, sir. I listen.
Yeah, sir has joined. Sir has
Good morning,
joined.
sir.
Yeah. Good morning, sir.
Good morning.
Good morning, everyone. I, Dr. Ram Kumar Kars, on behalf of the Department of Electronics and Communication Engineering, NIT Silchar, welcome you all to the TQ3 sponsored one-week webinar on recent trends in signal processing and communications at National Institute of Technology, Silchar, and Institute of National Importance, Government of India. This webinar is organized in association with Institute Innovation Cell NIT Silchar. I would take this opportunity to welcome you, our respected Director NIT Silchar, Professor Shivaji Bandopadhyay Sir, Dean Academic NIT Silchar, Professor A.K. Badhuria Sir, TQ3 Coordinator NIT Silchar, Dr. Sukumar Pati Sir, Head of the Department EC NIT Silchar, Dr. K.L. Vaishnav Sir, distinguished external and internal speakers, my dear colleagues who have immediately agreed to grace the inaugural session. I would also take immense pleasure in welcoming the participants from India and abroad to the event. About the participants and experts, a total of 1,538 participants have been registered for this webinar, out of which 1,528 from all 29 states of India, and the remaining participants are from 5 other countries, that is Canada, Bangladesh, USA, Oman, and Uzbekistan. There are 10 external eminent speakers, out of which 5 from academia and 5 from different industries. In addition, there are 7 internal distinguished speakers from signal processing and communication background. Now, I request the convener of the workshop, Dr. Rabul Hussain Laskar sir, to give an overview of the institution and theme of the webinar.
Thank you, Dr. Ram. Am I audible?
Yes, sir, you are audible.
Okay. Good morning, everyone. Respected Director Sir, Professor A.K. Badhuria Sir, our Dean Academics, Dr. K.L. Vaishnav, Head of the Department of Electronics and Communication Engineering, Dr. Sukumar Pati, TQ3 Coordinator, and dignitaries, esteemed faculty members, participants, and our student friends also. At the very outset, I would like to thank our coordinators, Dr. Ram, Dr. Ganesh, Dr. Chandrajit Choudhury, Dr. Ashraf Hussain, for conducting the webinar on recent trends in communication, signal processing and communication engineering from 10 to 14 September 2020. About the institute started its journey in the year 1967 as REC Silchar. Subsequently, the REC has been transformed and upgraded to National Institute of Technology Silchar with the status of deemed university in 2002. Finally, the Government of India declared the institute as an institute of national importance by enacting the National Institutes of Technology Act 2007. I would like to extend my sincere thanks to the Director, sir, for his initiative to promote the research activities and innovation at NIT Silchar. Under his strong determination and visionary leadership, we are able to reach higher and higher milestones in NIFR ranking, the World University ranking by Times Higher Education and other agencies. Now, NIT Silchar is visible in the band of 801 to 1000 across the globe. I hope under his visionary leadership, we will be able to bring more laurels to NIT Silchar in the days to come. About the webinar RTSPC-20, we have tried to cover two broad areas, that is communication and signal processing engineering. We have more than 1,500 participants, as my coordinator has already mentioned, and there are few participants from abroad also. We have tried to pull the experts from both the academia and industry so that the participants can get the feel about technical challenges in the industry as well. Anyway, the communication engineering is an integral part of our day-to-day life. Communication engineering includes various modes of communication such as radio, internet, satellite, broadband, wireless telephone services. The role of communication engineer is to design, develop, and be involved in the production of communication equipments. India is the world's second largest telecommunication market with over 1.2 billion telephone subscribers as of September 2007. The wireless segment dominates the market. India is the second largest country in terms of internet subscribers. The country is now the world's second largest smartphone market and will have almost 1 billion unique mobile subscribers by 2020. Revenues from the telecom equipment sector are expected to grow to $26.3 billion by 2020. India's telecom market is expected to experience further growth, fueled by increased non-voice revenues and higher penetration in rural market. On the other side, the signal processing is everywhere. It is not only limited to speech, image, or biomedical signal processing. It is equally required in communication engineering, VLSI design, microwave engineering, geotechnical engineering, control system, healthcare, robotics, and different various other areas. The classical feature engineering and shallow architecture-based approach has taken a backseat due to advent of deep learning techniques. Recent years, the signal processing technique integrated with deep learning framework is able to provide better than human label accuracy in various applications such as image classification, face recognition, word recognition, etc. It is reported that artificial intelligence has the potential to add $15.7 trillion to the global GDP by 2030, making the biggest commercial opportunity in today's fast-changing economy. For India, an incremental USD 957 billion could be added to the GDP by 2035, boosting India's annual growth by 1.3% point by 2035. So I believe there are ample opportunities for the people who are involved in the research, development, and innovation in the areas of communication and signal processing engineering. Having qualified and trained professionals in this field is the need of the hour. I think this webinar will provide a platform for our budding engineers and researchers, an opportunity to interact with the expert and professional in the areas of communication and signal processing engineering. This may help to excel further research in their professional development or further excel their professional development. Finally, I would like to thank our HODEC for his wholehearted support and cooperation, and especially the coordinators for conducting this webinar. I would like to thank all the faculty members of the EC department for their support and cooperation. I would like to thank our director sir and the TOKIP coordinator, Dr. S. Pati, for his and his team for providing the financial assistance for conducting the workshop. Hope the participants will enjoy the talks and it will give a great knowledge sharing platform and experience for every one of us. The world is going through a very tough time and we have learned to live in the critical situation. Hope the situation will be restored normal, back to normal. Thank you. Over to Ram.
Thank you, sir, for a good overview. Now, I take the privilege to request Head of the Department, ECE, Dr. K.L. Vaishnav, sir, to share a few words.
Very good morning to all. Our Honorable Director, Sir, Professor Shivaji Bandyopadhyay, all the Deans, Professor A.K. Borubuya, Professor M. Ali, Professor P. Patwari, all the distinguished speaker or experts, my dear esteemed colleagues, dear friends, and all the participants and delegates. On the behalf of Department of Electronics and Communication Engineering, we welcome all of you in this August gathering. The convener of the workshop already detailed about the workshops. I'm very happy to see the spectrum or the galaxy of these experts they have chosen or they agreed in the expert from industry, expert from academia, even expert from alumni also I see. And as we know that signal processing communication, already convener has given a brief about the growth of the telecom industry in India. Now, another challenge coming that people are moving toward the portable device. You want all communication in your portable device. As a result, signal processing for those small devices is very challenging. And you need to have your own processor or application specific. There are several sensors are coming up. Those sensors are touches with the real environment. It's called analog signal. And you have to process all those signal in a portable device. The signal processing and the BLSI for the signal processing is a very, very vital. If you see that we have a machine learning, so many things are coming, but you want machine learning maybe in a small device. So small device have a general purpose processor that may not be suitable for your application in terms of power, delay, many other issues are coming. So you have to have that you have that BLSI specific signal processor BLSI. I'm very happy to see that professor from IIT Delhi, Jayadaba, he is really excellent and is a good work also. The signal processing, BLSI for signal processing, they have a groove, I believe. I also see that the many of our experts from industry, because they are working on the real challenges. What is the market? Because market is so competitive, and to catch the market, you must be alert. What is the technology happening? What is the next future will come? Because the industry has to work for the future technology. They cannot wait. They cannot work on the present technology only. So because otherwise they have to, they will be losing the market penetration. Everyone want the better market penetrations. So the Galaxy expert they've taken, really, I am very much happy. Even we have a internal experts, as we already said that we have we started long journey already. Convener said we started from 83, and now initially we've been undergraduate courses, but over the really last 14 to 15 years we have given a big leap on this research activities, and today we are in the within the 800 to 1000 world ranking in terms of research institute. So we are now termed as a research institute, and that's really because after 2002 2004 it was a just undergraduate courses. We are not busy, or we are not focusing on the research. Now the institute is known as a research institute, and we must give to really that's congratulate to our director, Sir Professor Shivaji Bandyopadhyay. After his arrival to this institute, he has given emphasis on the research cultures, and which resulted number of foreign research projects. I mean, one day we never thought of international project. Now I think many people already got, and many projects are on the pipeline to have get the approval from the funding resources. Faculty are always agile on different agencies who are really funding. Yesterday also we have seen that the NTPC or Bharat Petroleum also seeking. I hope so that many of our colleagues really participate. That's really coming and motivating or stimulating the faculties to join to research and to take NI to the greater height. And if I see that the number of participants 1,500 is excellent for a workshop like this. Really, it is excellent. I hope so that because popularity is, in terms of popularity, it has gained a lot. Finally I must thanks to all the participants for showing their interest to be part of this workshops, and I believe that this 5 days they will enjoy to the greater extent. And we also look forward, because as many industry peoples are as expert in this workshops, we look forward to more collaboration with the industry, so that NIT research can be implemented or can be linked to the commercial products. That will motivate our undergraduate course students also, because undergraduate really their talents, as we already started undergraduate research council. That's is a good initiative. Nowadays our students really, we observe that they are coming toward the research culture or research mentality. So that will really, if industry comes, I think that really that motivations will be boosted up. So with this, I thank you everyone. If I'm not missing anyone, and I'm very happy to see that all my colleagues from communication background, really they have joined all together. That's really good sentiment that everybody joined over there from communication background. So with this, I must thankful to the TQ coordinator. Obviously, he's instrumental, because over the last 2 months, 3 months, is a wonderful number of workshops is happening, and that's all are really seamless and timely happening approval. So thank you, Dr. Poti, and welcome Dr. Poti this this sort of workshops. Without you, really, that could be not inspired. I understand the way you inspire the peoples. Finally, I thanks to the NIT administrations really for motivating all the faculties to be part of that and to invite, because that's really give the visibility to the institute across the globe. As convener said that some of the participants from the abroad really is a very good sense, and we want to take ourselves to the greater height and across the globe. With this, thank you all. Thank you all.
Thank you, sir, for your motivational words. I would now request Dean Academic Professor A.K. Badburia, sir, to share a few words.
Thank you, Dr. Ram. Good morning to all. Respected Director Professor Shivaji Bandyopadhyay sir, our expert guest, Professor Jayadeva from IIT Delhi, Head of the Department, Dr. K.L. Vaishnav, convener of this webinar, Dr. Arish Laskar, our TechIP coordinator, Dr. Sukumar Poti, other coordinator of these workshops. So first of all, I congratulate the coordinators and conveners for organizing such a beautiful workshop webinar on recent trends in signal processing and communication. Now, from the deliberation of the convener, it is found that a good number of participants are from outside the India also, and our experts are, a good number of experts are from industries also, in addition to academia. Now, regarding this topic, I am not very much conversant about this signal processing and communication, but one thing I can say, with the advancement of this communication, today we are able to organize this webinar in these critical, difficult days by sitting in different parts of the world. Students and experts are participating, joining this workshop. Now, regarding this workshop, our students, participants, and faculty members will definitely benefited and will come to know the recent developments in the field of communication and signal processing and scope for future research in this field. So our students, participants will be immensely benefited from these workshops, and they can, our newly joined research scholar may formulate their problems, research problem, so the discussion with the experts, and it will help the department, our research scholars, and this live problem even from the industry, they may choose their research problem, and which may lead to, as Dr. Vaishnav pointed out, some products also. So this scope, I wish our students will benefit from these workshops. And with these few words, I wish this workshop a grand success. Thank you. Over to Ram.
Thank you, sir. Thank you, sir, for your thoughtful words. Now, I request the coordinator of the TKIP 3, Dr. Sukumar Pati, sir, to share a few words.
Thank you, Dr. Hars. Good morning, one and all. Respected Director, sir. Respected Professor A.K. Badhuya, Dean Academic. Dr. K.L. Vaishnav, Head Electronics and Communication Engineering. The convener and coordinators of this webinar, my esteemed colleagues and dear participants. At the outset, I congratulate all the organizers, Dr. Arish Laskar, Dr. Ram Kumar Kars, Dr. Chandajit Chaudhary, Dr. Ashraf Hussain, and Dr. Ganesh Prasad for their initiative to conduct this webinar. I am sure that all the participants attending this webinar will learn the useful and relevant information about recent trends in signal processing and communication. I believe that this webinar will impart useful knowledge to all the participants so that they can promote research activities in the field of both signal processing and communication. Furthermore, the undergraduate students attending this webinar can effectively utilize the knowledge for their higher studies and future engineering career. I'm happy to share that most of the programs held during this current pandemic situation under TechIP 3, including this one, is now streaming live through official YouTube channel of NIT Silchar. I express my sincere gratitude to our Honorable Director Sir for his visionary guidance of opening YouTube channel. And it is heartening to share that in the month of August 2020 itself, the total views of our YouTube channel is 68,120 and the total duration of views is 13,558 hours. This statistic itself reflects the success of conducting workshop. I believe that through conducting a webinar like this, the peer perception about NIT Silchar can be improved to a greater extent. Once again, congratulations to all the organizers and participants. I wish a grand success of this webinar. Thank you.
Thank you, sir, for your kind words. I would now take the pleasure to invite our director, Professor Shivaji Bandyopadhyay, sir, to address the gathering.
Good morning, my colleagues at NIT Silchar, distinguished experts who are present in today's inauguration program, either in this Google Meet or in the YouTube channel, the PhD scholars who are participating, and other students also, both from India as well as from the different countries of the world. Now, it is really a good moment for us, that is from NIT Silchar. During this period of pandemic, we are able to organize such international level programs. That is when people are mostly bound to their homes or the safer places. So the dissemination of knowledge and discussions and moving further. So that is not stopping anyone to reach the next steps. Now, coming to the NIT Silchar situation, say we have put research and innovation as our key focus. And in that aspect, the 17 sustainable goals set by the United Nations, and which the government of India as well as all the countries in the world, they have identified that as their guiding principle. That is to identify areas where they will put their thrust on in their research and development. And by research and development, and when we say that, that is when the head EC was pointing out that we have the Undergraduate Research Council, and that was developed or built to inculcate the research culture among the undergraduate students. The idea was that it is not that every undergraduate student who will go for a research, as one of their, future career, but to see that they have the requisite research inquisitiveness in their mind, so that because the technology is changing so rapidly, so that whatever they learn during their course period, so they might become quickly obsolete, and new technologies and tools and instruments might be coming. But if they have the research inquisitiveness, so they get the idea of lifelong learning, that is how to learn a new thing very quickly, so that their adaptability to the new and the evolving situation. So that will be the fastest. And by that, the students from the NIT Silchar will be able to make a dent in the world environment as well. Now, when we talk about research, we basically focus about interdisciplinary, because in today's world, no research, no activity can be defined within the boundaries of a department. We need to study the basics. That is why the department structure we pursue in the higher education institutions, science and technology. But when we look into the practice, whatever be the courses also, so that people are learning machine learning across various departments, but every department looking into that aspect, which actually what kind of learning the systems need to do and so on. So interdisciplinary focus on research, collaborative, because the departments and the disciplines within the institute, any institute, they need to collaborate among themselves. And then at the national level, at the international level, internationalization is obviously one of the key factors to go ahead. because through internationalization and when you meet people from other countries, so the advantage is that you get an idea about the new kind of problems that the society in their country they are facing. Because every innovative solution actually needs an innovative problem. And unless and until we are acquainted with people from across the globe, we will not have that complete idea of innovative problems that plague the society. That is why internationalization is actually utmost necessary in its different forms. International students, international PhD students, international the research development projects, international collaborations. And then the fourth pillar of the research initiative is basically the industry. Traditional, the core industries, obviously in this region of the country, the northeast part, there are not so many. And obviously that is our focus when we talk about industry is basically the research focused industry. Industries which are oriented towards the future technologies so that our colleagues, research scholars, students, those who pass out, they can really contribute to these areas and not in addition to their already established contribution in the area of traditional core industries as well. Now, in terms of improving the research activities, say one strategy obviously is the undergraduate research council that we have identified. Another is basically increasing the number of PhD students. And over the last 2 to 3 years, we have basically doubled the number of PhD students who are working with our colleagues at NIT Silchar. The idea or the reason behind this is that is because the world is changing so fast and the state of the art, more and more research problems are coming. More and more interdisciplinary areas need to be worked with. For example, people who want to work in the biotechnology or the biomedical area, say, or the medical imaging and technology. Say, though we do not have a bio department or say the medical discipline, but we cannot stop our research in that direction because these bio area or the medical area, they are not the isolation areas. They are the science and the technology people have got a role to play. So we cannot be late in behind. So if we have more number of PhD students and because our colleagues are actually expanding themselves, so in order to carry forward those ideas, so we need more number of PhD students also. We are working towards more number of R&D projects, say the funds allocations that are increasing. And obviously that is as we go on and producing good results, so it has a cyclic effect. So more and more projects are bound to come. Now all of our efforts have obviously resulted in good set of rankings in this area of 2020 because the activities that we are performing for a long time, not only for the last 2 to 3 years, but since the inception of the institute, because everyone since the inception, they have a role to play. That is what NIT Silchar is currently today, be it in the area of infrastructure, be it in the area of teaching and the learning process, and be it in the area of the research and the innovation. So each and every people who got the opportunity to contribute to the NIT Silchar's development, so the current result of ranking and its continuous progress is basically a testimony to that. So already, I think my colleagues in India and maybe from abroad, they are aware through our website that in the national ranking for engineering colleges, we are in the 46th. In the national overall ranking, we are in the 94th position. In the innovation ranking, we are in the rank band of 11 to 25. And what Dr. Lashkar has said at the beginning, that is this year, we have featured in the Times Higher Education World University Ranking 2020 also. And obviously where the research-centric university is the key idea, so that as a technical institute and putting focus on the research-centric university to project ourselves, I think that is one of our acknowledgements also. Now coming to today's program on the say the communications and the signal processing, I think the core area of that in which this is basically an interdisciplinary area, And currently, that is in the country, in India itself. So, there is a national mission on interdisciplinary cyber physical systems. And say, why there is a relationship? Because everyone knows that in a cyber physical system, the inputs come from the sensors, which are distributed, which are varying. So the sensors collect different kinds of data. Speech data, sound, say the speech, the data, image data, then the video data, and different kinds of signals. It can be, for example, say if it is a flood monitoring system, then the level of the water, the weather reports, so on and so forth, and other issues. If it is a national highway movement, there is the traffic movement, so the nature of the traffic, the weather conditions, and other issues. So signals are captured by the sensors, and these data that is generated, they actually they fall in the realm of the big data because of their volume, the variety of the data, and the speed in which the data is generated. That is basically the veracity of the data. So all these big data that are generated in real time, and they have to be communicated or transferred to the computing environment engine, so that communication also becomes important. So the signal processing at the input, and then communications, the next step, then it goes to the processing part. And after the processing is done, so the real-time output is generated, and that goes to the actuators again. So the different sensors which collected the data, there will be a different set of actuators which will generate the output. So here, so the signal processing and the communication aspect, and along with that the processing capability, these three components together, they basically are the cyber physical systems. And in India at present, through the government initiative going for the last 2 to 3 years, so a 25 number of technology innovation hubs in the cyber physical systems, they have been identified. So the distribution of the technology verticals, they are obviously differentiated on the processing part. So the signal processing and the communication basically remains common to all the 25 technology verticals. Now, these technology hub institutions, along with them, a number of spoke institutes also, that is, which have their expertise and which have been tagged with the innovation technology innovation hubs. And NIT Silchar is identified as a spoke institute of the technology innovation vertical in the NMI CPS area, in the cognitive computing and social sensing. So that cognitive computing, social sensing focuses on the processing part, but the sensors and the communication part basically remains unique across all the 25 hubs that are there. So currently the different hubs, they are asking for project proposals to submit their complete DPR to the DST, Government of India, and in quick succession, in future, these hubs will be opening up their the call for research proposal to the other institutes also. So by these discussions, what I mean to share with my colleagues and scholars across this in today's program, say whatever may be the number, is that the future for the communication and the signal processing is going to be very bright, because with these two components integrated into the processing, so a lot of research project proposals are coming. That is, you'll have the opportunities to apply for that, to work in that. And at the same time, there is a research gap in this CPS area, because people who work in the signal processing, they work with communication. That is the maximum. Processing part, they have started working. But during the processing, the data that is generated by the sensors, so they are actually transformed or translated into the, say, comfortable data pattern, so that on which the processing can work on. But nowadays, people are working with taking the signal as the data itself. I give an example. See, in the case of speech-to-speech machine translation system, say normally when we have So it was that from speech that it was transferred to the text. Then the text-to-text translation took place, and then from the text also it was again translated back to the speech. Now, if we do the translation from speech to text at the very beginning, a lot of inputs actually goes out, and that kind of ambiguity resolution that machine translation systems need to do. For example, the different kind of pause and other signals, and the different additional utterances that we do while speaking. So sometimes having a confusion, say which word to use, then putting a thrust on a particular word. So these kind of inputs actually go missing when you do the speech to text transfer. So people are now working on the speech signal to the speech signal translation kind of work. So the people in the signal processing domain and those who do data processing afterwards. So instead of having a translation filter in between, so it is obviously utmost necessary, and the performance of such systems will increase if there is an integrated approach. So there lies the future of the cyber physical systems. There lies the future of those who are working in the area of signal processing, communication, processing, and that is the whole three components are basically interdisciplinary, because not only the people from the electrical circuits departments, from the CS and other areas, also application domains, civil, mechanical, they will also be involved in research activities and development activities in this communication and signal processing domain. So with these wishes, and I wish that during the next 5 days, these deliberations that will come up, they will contribute in a broader sense toward the national mission of interdisciplinary cyber physical systems, so that the initiatives at the national level can be fully exploited and can go beyond the country itself. Thank you once again.
Thank you, sir, for enlightening our knowledge with your encouraging words. Now, finally, I would like to request Dr. Ashraf Hussain, sir, for the vote of thanks.
Thank you, Dr. Ramkumar Kars. Respected Director, sir. Respected Dean Academic, sir. HOD, sir of EC Department. EKIP 3 Coordinator. Dear participants, esteemed colleagues, good morning to all. I am Ashraf Hussain, Department of ECE. It is my honor to give the vote of thanks. I must extend our deep gratitude to Director Sir for his motivation and support to conduct the 1-week webinar on recent trends in signal processing and communication, RTSPC-20. Thank you, sir, for your valuable words, and thank you for being with us. I must extend our sincere gratitude to all the speakers. We must thank to Dean Academic Professor A.K. Barhuya, sir, for his valuable talks. Thank you, sir, for being with us. We must thank EKIP 3 Coordinator Dr. S. Koti for his financial support. Thank you, sir. On behalf of the conveners, coordinators of this online 1-week webinar, I must thank our HOD sir, Dr. K.L. Vaishnav, for his continuous support. I must extend my thanks to all the participants for showing their interest in this particular topic. I must thank our esteemed colleagues. I must thank the conveners of the program, coordinators of the program for the initiation to organize this 1-week online webinar. Finally, I must thank Dr. Naresh Babu, CSE Department, NIT Silchar, and other technical staffs of Central Computer Center for live telecasting this program on NIT Silchar YouTube channel. Thank you for all for being with us, and thank you all, and over to Dr. Ramkumar Kars.
Thank you, sir. Thank you, everyone, for gracing this inaugural session with your kind presence. With this, I would like to conclude the inaugural session. And dear participants, thank you, sir. And dear participant, We will start with our very first expert lecture at 11:35 a.m. It will be delivered by Professor Jayadeva, IIT Delhi, on the topic Learning Complexity Controlled Neural Networks. Kindly request you to use the same YouTube link for your next lecture.
जी सर। वो कभी शायद पता नहीं क्या, मैं पूछता हूँ एक बार सर, कंफर्म कर रहा हूँ। अभी अभी कॉल बैक।
Okay, sir.
हेलो।
Professor Jaydev. Hello.
Yeah, hello.
गुड मॉर्निंग प्रोफेसर जयदेवा सर।
Good morning. I couldn't hear
Network
anyone
can
till,
hear.
I couldn't hear anyone till now. I think the mics were muted.
Yes sir.
Yeah, good morning, sir.
Good morning.
Yes, sir. Uh, Once again, good morning to one and all. Now, I would like to welcome you all in the first session of this webinar. I would like to extend my deepest gratitude to our honored speaker, Professor Jaydeva sir from IIT Delhi. Now, brief introduction about the Jaydeva sir. Professor Jaydeva sir received the PhD degree from the Indian Institute of Technology, Delhi in 1994. He is a professor with the Department of Electrical Engineering, Indian Institute of Technology, Delhi, where he currently holds the Microsoft chair. He is a recipient of awards from the Indian National Academy of Engineering and the Indian National Science Academy. He was a URSI Young Scientist at the General Assembly in Lille, France in 1996 and received the Sir J.C. Bose Young Scientist title from the Indian Council of the URSI. He has published an ample number of reputed journals, book chapters that have very good citation. He has been issued 2 US patents. He is an author of the book Numerical Optimization and Applications. His research group was among the first to fabricate an SBM-based application for very large-scale integration ASIC that contained an AD converter using a bank of analog SBM classifier. Professor Jaydeva sir is an associate editor of the IEEE Transaction on Neural Networks and the IEEE Transaction on Cybernetics and other reputed journals. He has served on the steering and several international program committee. Now, with this, I request you, sir, to present the talk.
Yeah. Thanks for the introduction, although it's a bit dated. I think the CV is a bit dated, needs to be corrected. Anyway, let me. I hope I'm audible.
Yes sir, you are audible.
Okay. So, all right. Are you able to see my screen?
Yes sir.
Yeah.
Yes, sir. It is seen.
So anyway, please stop me anytime you needed to if you want to ask something. So just a correction, I'm not Microsoft chair. I'm holding now the institute chair professorship. So okay, but anyway, let's start with the topic itself. So we now have seen deep learning takes center stage in machine learning and AI, and deep learning is now almost the method of choice for a very, very large number of applications. It is also known that if you look at most deep learning architectures, the number of weights or synapses in the neural network is often much larger than the number of samples in the data set. So in other words, you have more variables to optimize than the complexity of the data set itself. So it's difficult to interpret what the network actually learns. These take a long time, and additionally, one would like to implement these, say, on embedded intelligence systems or smartphones or IoT devices, and then the size of the model becomes very important. So what we look at is a bit of work that we have been doing over the last few years in the direction of how to control the complexity of models, or how to learn simple models in neural systems or neural networks, but not just in neural networks, also in kernel methods. So I'll start with complexity control in kernel methods, from where this work started, so that it gives an idea of what the motivation for this is and how the approach originally started. Okay, so to start out with, let me show you an anecdotal slide. And this is, the question that I usually ask with this slide is, what's wrong with this picture, right? So this, of course, you can see, well, in straight terms, you might have an answer that there's nothing wrong with this image, because it's perfectly fine. I mean, people are getting to their destination a lot of the time, traveling in this fashion. So in some sense, this might even be routine in some circumstances. But what we also recognize, and that's really the answer to this question, is that if we the answer to this question essentially is that while there may be nothing really wrong with this, but there is a high risk of failure. So in terms of the chance of an accident or chance of failure of this model or the situation is much higher probability than, for example, if we had a bus in which people were safely seated inside, and so that would be a safer situation. So in a similar sense, what happens in machine learning models is that if we have a large number of degrees of freedom, and we are occupying or using all of these degrees of freedom, the likelihood of failure on data that we encounter or situations that we encounter in the future is high. So in other words, what we would like to have is a situation where we have a small number of degrees of freedom, but just enough to be able to handle the situation or the data that we are encountering. And so that is the trick. The trick is, how do you keep the size of the model just enough to be able to handle the situation that you need to handle, which is the learning problem that you have encountered. So let's look at these two pictures here. So what I'm showing you is, it's just a sketch. It's not actually a let's say it's not actually a real diagram. It depicts a situation in which there are, let's say, a set of samples, and there is a hyperplane or a or a plane or a line in this case, that's separating two classes or samples of two classes. Now, what we are saying is this is in high dimension, and so this is not really a 2D sketch. We also are saying that visualize that the number of support vectors is the same. So you will see the samples that are close to this hyperplane, they're exactly the same. The closest samples are exactly 4 in number. They are at the same distance, so the margin is also the same. And the number of training samples, so total number of samples on either side, is also the same. And so the question is, if these are identical in all these respects, which of the two, if at all, is likely to have a lower test set error, right? So is it possible that one of the two has a lower test set error than the other one? And so so I'll leave you with a minute to just think about it, or half a minute to think about it. So we are saying the two are identical, except, as you can see, on the right side, the samples are spread out a little bit more. And on the left, the samples are kind of contained in a smaller region. The answer to this question actually is that the test set error is likely to be lower for the diagram on the left, or the sketch on the left. And in intuitive terms, this is because if you look at the neighborhood of any sample, you'll find that, or if you look at, if I put a test sample somewhere, so let's say I put a test sample here, and in the neighborhood of this test sample, you at least will find some other samples which give you an idea what the class in this neighborhood is likely to be. Whereas over here on the right, you find that you really have a lot of empty space. So you don't have enough evidence to really claim that this might be a sample in the yellow class. Well, you don't know. You could be wrong in both cases, but the chances you are right are likely to be higher for the example on the left. So in some sense, as you can see, the spread of this data set, or the radius of this data set, has something to do with the probability of error on test data. So let's move to the next slide and show you that. And what you see here is probably the only complicated formula I'll show you. And what this says here is that, this is Vapnik's risk formula. Vapnik did most of the work, a lot of the, very seminal work on, learning theory, computational learning theory. And what he said is the probability of error on test data, or on the complete distribution, is upper bounded by probability of error on the training set, which makes sense, which means that if you do better on the training set, your error train is smaller, the chances you will do better on the test set are also higher, right? But there is a second term on the right side. So this upper bound on the error you'll make on test data or on the overall distribution is actually upper bounded by a second term. And the second term contains, something as you see here, this B epsilon. This term has an expression here, which we are calling VC. And VC is the Vapnik-Chervonenkis dimension of a classifier. So basically, this is a measure of the complexity of the model. So what this says is, and you can see roughly, if you took epsilon and looked at the term here, you see this is a root epsilon term in the denominator. So approximately, you might say you will get a root epsilon term inside the brackets. So what it means is, if VC is large, then the probability of making error on test data is going to actually become higher, not because you're doing badly on training data. You might be doing very well on training data, but because your VC dimension is large. And the VC dimension is the measure of the model complexity. So if you can somehow keep model complexity low, then you will tend to do better. And what it also says is that given two models that have the same training error or same training accuracy, if there is a model with a smaller VC dimension, it will actually be better. So I won't go into mathematics of VC dimension, but roughly you can think of it like the degrees of freedom of the model. It's not precisely correct, but that's roughly the way I will use to explain the rest of this presentation. So in neural networks, the VC dimension depends on the number of weights or number of synapses and number of neurons. So pruning of neural nets reduces the VC dimension. So techniques like dropout and drop connect, are actually effective in doing that, and that's why we use them to keep the VC dimension low. In support vector machines, the number of support vectors is actually a measure of the VC dimension. So, but fewer support vectors leads to better generalization. But technically, if you go a bit deeper, you actually get to learn that SVMs can have infinite VC dimension. In other words, with support vector machines, it's possible that the model complexity is not bounded. And this is something, I'll show you a bit later in this presentation, that it's a bit of a surprise when you encounter it. And you can try out this experiment yourself. Please stop me anytime you have a question. Taimur, you are able to hear me, right?
Yes, sir. Yes, sir.
Yeah. So anyway, please encourage anyone who wants to ask. You can ask even in between. I'm okay with that.
Sir, it will be better if the students or participants would ask in the end of your lecture.
Sure. Okay. Whatever way, you're the you're the expert conducting it, so that's fine. Right. Absolutely okay.
Yes, sir. Yes,
okay.
Sure.
So let's look at this a bit more. So basically, what this says is that use the simplest solution for a given task. And how do we go about doing this? So the problem is that, if you were to look at how does VC dimension vary with the parameters of your learning machine or the variables you're optimizing, you might want to draw a curve like this and say, let's find the minimum of this curve, with some requirement on being able to fit the data that's given to us. So it turns out you can't really draw this curve. The VC dimension is it's an abstract, it's a mathematical, kind of concept, but you can't really relate it directly to the variables you're optimizing, at least most of the time. And so this curve can't be drawn, and as a result, optimizing it really hasn't been accessible to us in a very convenient fashion. Okay, so it turns out that Vapnik and actually then Burgess in his tutorial expands on it a bit more. They said that the VC dimension is upper bounded by this expression, which is this is 4r squared by d squared. I'm sorry, this should not be n squared. I'll just correct this. It should be n. Sorry. Just 1 second. I think we. Okay, I'll actually do it at the end. So it's okay. Okay. So this should be 4r squared by d squared, comma n plus 1. So n is the dimension in which the samples lie. R is the radius of the data set, and d is the margin. So this is a result that uses a notion of what are called fat margin classifiers. But suffice it to say, for our present discussion, we're essentially saying that this upper bound depends on the radius and this margin. And what you would like to do is, you would like to say, if you want a small VC dimension, you need, this quantity to be small. And if the number of features is small, well, that's anyway good for us. But this is the smaller of the two. And most of the time, we will actually find that because our data is in high dimension, the smaller of these two is r squared by d squared. And so you would like to keep r squared by d squared small. That means that, if you think about it, given a data set, r is possibly a constant. And so this means keep d or the margin as large as possible. So that means maximizing the margin. Right. Okay. So we look at it a bit more. Okay, well, let me come back to it a second. But actually, as it turns out, r is really not a constant. And the reason is that if you look at this data set here, what I could do is by applying a linear transformation or some other transformation, I could change r. And if I did that, I could, let's say, move from the situation on the right to the situation on the left. And the margin would not be, would not shift in the same fashion. So in other words, the margin depends actually on r. So this is not really a situation where r squared and d squared don't have a dependency on each other. And therefore, you really would like to minimize the ratio of the two. So R really is not a constant because you can always pre-scale or apply some pre-processing to the data to change R, and thereby influencing D as well. So in SVMs, this is what we do. We maximize the margin and we assume that the radius is a constant. So we are just saying the distance of the closest sample from the separating hyperplane needs to be as large as possible. Okay. So what we did in this work, that's the starting point of the discussion. We showed that if you have a hyperplane u transpose x plus v equal to 0, then the upper bound on this, so one upper bound on the VC dimension of that classifier is something like this. It's max of u transpose xi plus v. So what does this mean? This is the distance of the furthest sample, the sample that's the furthest from the hyperplane, and the denominator is the distance of the closest sample from the hyperplane. So what this is saying is the ratio of the furthest sample to the closest sample. This distance is actually gives you an upper bound. Actually, h squared is the upper bound, and h is this is this expression. So we did some algebra and some optimization on this, applied some optimization theory on this. This is a fractional programming problem, and we reduced this to a linear programming problem. And this is the linear programming problem that we solve. So I'm skipping the maths at the end. If someone is interested, we can look at that. But what this is saying is, if you look at this, this is saying that all samples need to be separated. That means for samples of class 1, where yi is equal to 1, w transpose xi plus b should be greater than 1. That means the samples should be at least a distance of 1. If yi is minus 1, that means class minus 1 samples, then w transpose x plus b should be less than minus 1. And this is again saying samples of class 1 should be at a distance of 1 or more. Samples of class minus 1 should be at a distance, sign distance of minus 1 or more. So this is exactly like the constraint you find in support vector machines. But the second part of this is actually the kind of the distance of the furthest sample on either side. And the objective function says minimize this distance. So what does this actually mean? It means don't just maximize the distance of the closest sample, minimize the distance of the furthest sample. And you can see that intuitively what it means is, if you had a sample that's far away and like an outlier, if you somehow moved it close to the other samples, the probability of making a mistake in this empty region in terms of classifying some sample, like a test sample, would actually be lower. Okay, so of course, this was the hard margin classifier. So just like with support vector machines, what we say is, well, all these constraints could be satisfied with some error, and that error or slack variable is qi, and if you add that, you get this, this soft margin classifier. So this is the minimum complexity machine soft margin classifier, and what this is actually able to do is that this is solving a linear programming problem. So you can see there is no quadratic expression, there is no qi squared, there's no h squared. It's a linear programming problem, and all the constraints are linear. So it's actually much simpler to solve than SVM. And let's see, let's go further. This is of course possible to use when, for instance, samples are linearly or approximately linearly separable. Right? What happens is that let's imagine if you have a more complex situation. So if you have a complex data set like this, then you really can't separate them with a straight line. So you might want to say, let's use a nonlinear decision boundary. And if you want to look at that, that means want to look at a nonlinear curve or some other expression. But this is a difficult thing to do. So, you want to solve a nonlinear system of equations. It's not mathematically very tractable or very appealing. So what should we do in such a situation? So we have a small trick that we can employ, and this is illustrated with the XNOR gate. So you have samples of class 1 as crosses and samples of class 0 as these filled red circles, and you can't separate these two with a straight line. So one way is, let's look at these samples as if they are lying in 3 dimensions. And right now, the third dimension is the same for all of them. We don't have any more information than previously. But let's suppose I could add a third dimension in some fashion. So, and we do that by, let's say, applying a nonlinear expression. So let's say we said Z1 is X1, Z2 is X2, and Z3 is X3. It's 2X1 minus 1 into 2X2 minus 1. And if you did that, the sample which is at 0, 0, which is here, the first 2 coordinates are the same. So that's 0 and 0. The third one becomes 0 minus 1 into 0 minus 1. There's minus 1 into minus 1, so it becomes plus 1. Similarly, the sample at 0, 1 moves to 0, 1, and minus 1, because this is 2 into 0 minus 1, this is minus 1, and 2 into 1 minus 1 is plus 1. So third coordinate is minus 1. And then the sample at 1, 0 stays at 1, 0, and minus 1. And the sample at 1, 1 moves to 1, 1, 1. Right? So what this is actually doing is, you can see that the blue crosses have actually moved to a plane which is different from the plane in which the samples of class of the red samples lie. And so it's very easy to separate them now. So what you can see is, we could just put a plane in between, and now the problem that was not linearly separable has become linearly separable. So this is essentially the trick of transforming the input samples into a higher dimension using a nonlinear function or a nonlinear map. So instead of trying to find a nonlinear separator, we transform the samples using a nonlinear map into a higher dimension and use a linear hyperplane to separate them. Right? And that idea gives us the MCM soft margin classifier. So we are seeing that what we can do here is, you can say, okay, we had the same expression as before. Instead of xi, which is the ith sample, we've written phi xi here. And what that really is saying is, I'm taking the samples xi and transforming them to a higher dimension using this map called phi. And W transpose phi gives me, so the hyperplane in the higher dimension is W transpose phi xi plus. So this phi lies in some higher dimension as compared to the input samples xi. The second constraint is exactly like before. So all we've done relative to the previous expressions that we had, in place of xi, we've just written phi of xi. The thing is that we don't want to actually know what is this phi xi. So, we don't want to actually explicitly use phi, because you might be wanting to take input samples from, let's say, 2 dimension to 100 dimensions. And you don't want to work with 100-dimensional vectors. So we use a small trick, and that trick, I'm happy to explain it, in case some of you don't follow this, but I'm assuming you're familiar with SVMs and so on. So these image vectors form an overcomplete basis, and so we can write W as a linear combination of the image vectors. So we call them image vectors because the samples xj are transformed into phi space into image vectors phi of xj, and W is W is the hyperplane coefficient vector that also lies in the same space. So this is what we've done here. Okay. Well, if you write this down and you put it back into these equations and you use what's called the kernel trick, you get an expression which is essentially, it uses what's called a kernel function. So once again, we have a linear hyperplane. We are solving for a linear hyperplane. We are solving for a bunch of coefficients lambda. we are still solving only a linear programming problem. So the nice part is I can just use, I don't have to use a quadratic optimizer. A linear programming solver is enough. But some other interesting consequences emerge out of this. Normally in SVMs, you can only use positive definite kernels. But over here, we can actually use all kinds of kernels. And we've actually shown that using this can give you benefits. So you can use, for example, a kernel like a sine wave function, which is impossible to use in a normal situation. So what are we expecting out of all this? We are saying, what did we start out with? We said if we do this, then we should be able to minimize the VC dimension. So what actually happens in practice? Let's see that. So I'll let you study this table for a little bit. What we've done here is we have run the minimal complexity machine and we've run support vector machines on the same data. And these are 5-fold cross-validation results. So we've taken the same data set, the same training and test splits, and of course that's done 5 times, and what you're seeing is the mean accuracy and standard deviation, the CPU time, and you're also seeing the number of support vectors. Okay. So what happens is you can see here, for example, let's take the first data set. You're getting an accuracy of 89% with MCM, and you're getting 88, about the same accuracy with SP. So accuracies are about the same. If you see the column on accuracy here and the column here, they're about the same. Most of the time, you'll find MCM slightly better or comparable, sometimes slightly worse. But let's look at the column on number of support vectors. So number of support vectors is, what's the size of the model? And that's the number of lambda j's in the previous expression, which are non-zero. So you see here, I just have about 10 support vectors. Here on an average, I've got about 38. And let's look at this data set here, the Hayes data set. You see, I'm only using about 3 support vectors. And here I'm using about 84. So this model is almost like 30 times bigger if I used SVMs as compared to the MCM. Let's look at this. This ratio of 10 is to 124 to about 12. And here you see a really large ratio. You see on some data sets, I'm using like 3.4 support vectors, about, let's say 4. And here I'm using over 400. So I'm actually using 100 times bigger model to achieve the same accuracy. So this is important if, for example, you want to train a model on something and put this model onto, say, an IoT device or a smartphone or some other embedded platform where you have a small amount of memory, you want it to run quickly, you don't have too much of CPU time to use or CPU resource to use. So the size of the model becomes very important. So for instance, if I had a model with only 4 support vectors, I just need to use something like 4n computations to determine the class of a test sample. Here I need to use 400 such computations. So I would take 100 times more time as compared to the model here. Right? So it's actually very beneficial to use small models when you are trying to put them on resource constrained platforms. So the general observation is the MCM uses about 1/3 the number of support vectors. Sometimes this is 1/10, and sometimes it can be as large as 100. Okay. Let's go a bit further. What more does this imply, right? So first of all, we don't have to use quadratic programming. We can use linear programming. Number of support vectors is small. There's no issue of conditioning of the SCM. So numerically the MCM is actually more appealing, and it can use all kinds of kernels. But there is a drawback. The drawback is because it's a smaller model, the hyperparameters that are there, for example, C, you need to tune it very carefully. You need to tune it much more finely than an SVM. And this is understandable. If you have fewer parameters governing the solution, those parameters become more important, right? there is some further observation. So this is a very interesting plot, and this actually tells you, shows you VC dimension in practice. So what we've done here is we've got a data set with about 50,000 samples. 25,000 of them are from a training set, and 25,000 of them have been put into a test set. And while training, what we are doing is we are taking 1,000 samples at a time, learning a model, and then adding another 1,000, training it. Then so we increase the size of the of the training set by 1,000 samples each time, going all the way to 25,000. And of course, we are assuming the accuracy is same as the SVM. We are trying to compare the SVM and the MCM in terms of the size of the model. So on the y-axis, you see the number of non-zero weights. This is a linear MCM, no kernel used here, and number of non-zero weights is on the y-axis. So what you see here is, as I'm increasing the number of training samples, the size or the number of non-zero weights is just going up all the time. It's going up actually almost linearly, which means that if you kept having more data, the size of the model would keep growing. And basically, the size of the model is not bounded. But look at MCM here. What you see is something very peculiar. You're seeing the size of the model initially grows. And that's understandable because you're adding more data, so more information. But then the size of the model starts to go down, and then it saturates at some point in between. And the reason this is happening is that as you encounter more data, you actually have more representative samples. So what's also happening is that you're going to get not just more data doesn't just mean more samples. As you have more samples coming in, some of these samples are more informative. They contain more information about the data set or the distribution than other samples. So for example, samples lying near the decision boundary are more informative. So if you had a model that's trying to keep the complexity low or minimize the complexity, it's also trying to keep the most representative samples or the most, let's say, important bits of information as part of the model and discarding the rest. And therefore, you see that later on, as you have got more informative samples, the model could actually be reduced in size compared to somewhere in the middle, right? So this actually shows you that in the case of SVM, if you remember, I remarked that the VC dimension of SVMs can be unbounded. What this is saying is, if you give me more and more samples, I might be able to keep the accuracy under control, but accuracy might still be good, but the size of this model will just keep growing, right? And that's not a great thing if you're learning in the field or if it's lifelong learning. For example, the data is coming all the time, and you don't have the luxury of saying, I'll keep increasing my hardware or the amount of memory I have indefinitely. So, let's look at something else. Taimur, would you like to take a break in between for a minute or two or whatever, or you want to continue uninterrupted?
That is up to you. If you require, you can take a break.
No, I don't need a break. I just want to have a glass of water. So I just stop for a second.
Okay, sir, no problem.
Yeah, Taimur, I'm happy to continue if you want. Hello?
Yes, sir. Carry on.
Shall I go ahead or?
Yes, sir. Go ahead, sir.
Okay. All right. So let's look at another angle to VC dimension. So turns out the number of features used by a linear hyperplane classifier is VC dimension -1. So what you can do is, if we run the linear MCM, the number of non-zero weights, the features for which the weights are non-zero, actually give us a list or a collection of features that together are able to produce a good model, right? So in other words, you can use the MCM also for feature selection. So feature selection is a difficult problem because it's not necessary that the most relevant feature, the most discriminating feature, is part of the most discriminating set. So if I asked you, give me 5 features that are the most important taken together, they may not include the single most important feature. You know, the 5 together might have more information and might be together more effective than the single most important feature. So what you see here is we've done the following. We've run the linear MCM and found those features for which the weights are non-zero. And we've taken those, and then we have trained a support vector machine using those features. Similarly, we have collected 2 other methods. One is called ReliefF and one is called FCBF. We have selected features from that and then trained a SVM. And what you see here is, you see that the MCM can give you similar accuracies with very few features. So it's doing a pretty good job of feature selection. So here is a data set. For example, most of these data sets are genomic data sets. It's like saying pick the smallest set of genes that describe, that can distinguish between one class and another class, right? And you see here, for instance, the last one has got 102 samples in 12,600 dimensions. So there are 12,600 features and 102 samples. And we can just pick 81 out of the 12,000 samples and get similar accuracies as, let's say, FCBF, which is using almost all the 12,000 features. It's using just 1,000 less, but essentially it's using almost all the features, and you can get similar accuracy by just using 81. So in situations where you want to target, let's say, a small set of genes or small set of variables in order to do something, like, for example, for drug discovery, you want to find a drug that enhances or suppresses the expressions of specific genes. I only have to worry about 81 here. I have to worry about 11,000 plus here. So it's, it significantly simplifies the process of drug discovery. Okay. So anyway, at the end, please do ask me on the slide if you want me to expand more on this. So why did we do all this? Nobody really uses kernel methods anymore, right? Everybody is looking at deep learning. But what became possible is, once we had a linear programming problem, and once we had an optimization problem that we can solve, let's say, conveniently, and which we can analyze, what we could do is we could take it to neural networks and deep learning. So, which is what we did. And I'm just putting this data set, the slide, sorry, for those who have interest in the maths for it. So given a linear programming problem of the kind on the left, there's a primal, and the linear program also has a dual. So the left you see the primal, the right you see the dual. And basically in an LP, the two will converge to the same solution. There's no gap. What we do was, if we have a linear programming problem to solve, it turns out you can build a set of differential equations, and that's what we term as a neurodynamical system. This is a set of coupled differential equations in the primal and dual variables. So the primal variables are theta, and as you see here, primal variables are theta here, right? And here the primal variables are delta. And so we are looking at the primal variables change using this equation, which depends on the dual variables and their rate of change. The dual variables change depending on the primal variables and the rate of change of the primal. So they are coupled, and both of them will actually converge together. So if I have a linear programming problem, either the primal or the dual, I can build this system, and what I end up doing is I end up using this as if these are corresponding to the changes in the weights of a neural network. So that's so we took this minimal complexity machine linear programming problem, and what we did, we converted it to a standard form. Okay, and this paper actually has just appeared online. Just in fact this month. So you can take a look at it. And what we do is, so let's look at this example here. It's a simple two-dimensional synthetic data set with a class of blue samples and a class of red circles. Okay, and if we look at this, so here is what you see here on this graph is, there are two coefficients, W1 and W2, corresponding to the input variables X1 and X2, and you see the plots of W1, W2, and W1 dot, W2 dot. So you can see the weights are converging to set of values here, right? The weights W1 and W2 are converging, and they're converging together. W1 dot and W2 dot both converge to 0, which means they have reached a steady state value. Okay. Here, W1 on the left, essentially one of them, the W1 has essentially gone to 0, so you can really only use W2. W1 is almost 0, right? And here is the offset B. So, right. So your hyperplane is W transpose X plus B equal to 0, and in 2 dimensions, that's just W1 X1 plus W2 X2 plus B equal to 0. So let's look at how the VC dimension moves. So here the VC dimension moves to a value 1, which is actually, or bound, sorry, not really the VC dimension. The bound moves to a value 1, which is actually the smallest value it can get to. So H also converges in the same fashion. Okay. So what does this look like? Well, this neural network looks like this. What we've got is, we've got a, at the output layer, the final layer, we have the changes in the primal and dual variables. What we've additionally done is, we have backpropagated the weight changes in the last layer backwards to the previous layers. So this is a bit more than just the MCM, because what this is also doing is it's modifying the map that is formed in the previous layers. So it's actually more powerful than the MCM itself. It's optimizing the final layer to find the classifier, but it's also modifying the map formed by the previous layers of weights. Okay. So here is a table that actually shows you, what is the the way in which the these different methods, how do they compare with each other. So what you see here is, we have the linear SVM, we have a kernel SVM on a number of data sets, right? And there's a typical, a standard regularized neural network, feed-forward neural network, the MCM linear version, the MCM kernel with RBF kernel. There's a technique called twin SVM. We use that, and of course the MCM with a neurodynamical system, which has the added advantage that it's also optimizing the map, which means it's also optimizing the kernel. And you can see the MCM NDS does actually quite well. In fact, in most cases, it does as well or better than any other method. So it actually has an advantage. These are small data sets. These are not very big data sets, but let's look at something bigger. So you can see here, for example, these are roughly about 80,000, 70,000 samples and so on. We could do even bigger, but these simulations are done just on a laptop. And so here also you can see that, in fact, results are quite comparable, right? And in most cases, or it's comparable or actually sometimes better. So remember, we said the weights in a neural network usually outnumber the number of samples, right? And let's look at what happens if we use MCM-based learning methods on neural networks. So this slide actually is a comparison between a situation where a neural network is trained with the MCM based learning rule, and on the right side you have the same neural network trained with a standard learning rule. And what do we see? So we see 3 or 4 very important things. First of all, you note the peak of these 2 histograms. So there's a histogram. The x-axis shows you the values of the weights, and there are these bins. So the height of the bin is really how many weights do we have lying in that bin. So first of all, what you see here is on the right side, which is a standard neural network, you see that the area under this curve is much larger, and that indicates that most of these weights are non-zero. So a lot of weights that are non-zero, indicating that the network is not sparse. On the left side, you see that pretty much the spread of weights has been contained. So there's a narrow spread of weights, which means most weights are now actually 0 and small. So you see the peak around 0 is almost 3 times the peak on the right side. So here the peak is about 1400. So there are roughly 1400 weights around 0, well, to the left of that, and so on. Here you see that just at 0 itself, it's almost like about 3000. So it's almost 2.5 times what you see on the right side. So most weights have actually become 0. The small number of weights that are non-zero, and you'll also see that, in fact, the number of weights that are significantly away from 0 is actually much smaller than for a standard neural network. So if you actually look at how many weights are non-zero, you will find that we reduce the number of weights from something like 80,000 to something like 300. So this neural network was trained on the MNIST data set, which is a handwritten character recognition data set. Let's also look at what the neural network learns. We look at the features that are there inside the neural network. So the features look like what are the receptive fields of the neurons inside the hidden layers. If you see that, you will see here, for example, this is the left side is the MCM based learning rule, and you see that these are very high contrast. So in other words, and that's because the weights are either clearly 0 or they're at like some kind of peak value. On the right side, you will see that there's a lot of gray, indicating that most of the weights are non-zero, and it's not like you have clearly defined features that are used. All features kind of play some role, and some features are slightly more emphasized, but you can clearly see the features on the left side are very strongly delineated. Right. So this kind of the purpose of showing all this was to say the following things. So one, you can learn very sparse models. From 80,000 to 300 is almost a factor of 300. You can learn, you can take these methods by building the optimization techniques in the kernel domain and moving them into the neural network domain. So now you have clear-cut and well-defined objectives that you're optimizing. You know how you can prove convergence, and you can study what properties the emerging model is going to have. You can see the features that these learn are very clearly demarcated. You can also see that the generalization of these models improves. And even in kernel methods, we also see that even when more data keeps coming, it's not that the model size keeps increasing. The model size is contained, and we are able to actually learn effectively even with that. Okay. So what I'll do is, I think, Taimur, I'll just stop. I'll just give you a list of references here, and leave some time or ample time for questions, because I think that's where at least some thinking gets provoked. So I will stop at this. And Taimur, would you like to just moderate the questions in some fashion, right?
Yes. Yes, sir. First of all, thank you very much, sir, for your wonderful talk. And prior to that, I am very much thankful on my personal behalf, as well as from the organizing committee behalf, that you have spared your valuable times for us in spite of your hectic schedule, that I know it very well. Now, coming to the queries based on YouTube link, that first query is, what is the ratio of training set and testing set in a neural network model? Is there any standard algorithms available to pick up number of training sets and number of testing sets in a neural network model?
You mean training samples, right? Number of training samples and number of test samples. I suppose that's what he means. So what we have done, I mean, it's one way to do it. So what we typically have done both in the kernel methods and in the neural network one, we have taken. So let's say you have a data set with m samples. Let's say m equal to 100. So if you have 100 samples, divide it into 5 equal parts randomly, or k equal parts.
Okay.
These k parts are called folds. Now we train on k-1 folds and test on the remaining one. Now, if you've got 100 samples and you've got 5 folds, k is 5. So each fold has 20 samples. You train on fold 1 to 4, that is the first 80 samples. Test on the last fold, which is 20. Then you train on fold 2, 3, 4, 5. Again, 80 samples. Test on fold 1, which is 20. So you do this 5 times. And in the general case where k is something other than 5, you do it k times. Each time you will get some accuracy on the test set. So you take the mean of all of these and you compute the standard deviation. So if your mean is small, that, or sorry, if you are, well, depending on whether you're talking about error or accuracy, you want the error to be small. So you want the mean to be small, and you want the standard deviation also to be, well contained. So it gives you an idea whether the model is overfitting or not. It gives you some information about that. That's what. So this technique is called k-fold cross-validation, and that's what we usually do. So that's, we've taken k equal to 5 in our case. Yeah. Okay.
Yes, sir. Sir, next query is, how will you differentiate the term SVM with SVR?
So
support
SVM
vector
is,
regression with support vector machine.
Yeah. So support
both are
vector
same
machines,
or having some different?
Yeah. So support vector machines, are a general technique. The original, method is essentially to do with classification, and then it was extended to regression. So SVR refers to regression. SVM typically refers to classification, although sometimes we use SVC to denote classification. But generally speaking, SVM will deal with classification. SVR will deal with regression.
Okay. So next query from my side is, what do you mean by support vectors in a SVM? Why these are called as support vectors? Why?
Okay.
What do you mean by support vectors in SVM?
Okay, let me try explaining that. I'll have to draw a bit to be able to do that. So let me see if I can do that actually. Yeah, just give me a second. I'll put a blank slide there and that'll be easier.
Yeah.
I hope you're still seeing the screen, right?
Yes, it is visible.
Yeah. Okay. So basically, if you look at support vector machines, you'll find the weight vector W is given by summation I equal to 1 to m lambda I. So here xi is the ith sample, yi is the class label. So yi belongs to 1 or -1. Okay, and lambda I is a Lagrange multiplier.
Yes, sir.
Right. Okay. So now you can see that. So what happens is the Lagrange multipliers lambda. So these lie between lambda I lies between 0 and c. Okay. So some of these lambda i's could actually be 0, and you can see that in that case. I'm sorry, this is just a bit. I need the eraser here. Okay. So you see that in fact what's happening is that, yeah. So if lambda I is 0, then xi has no role to play in determining w, right? And that actually means that the only xi's that matter, the only samples that matter in determining w are the ones for which lambda I is non-zero. So the word, if you see the support of a function, okay. So you can see that w is a function of the xi's. The support of a function essentially is the region over which essentially it would be non-zero. So in other words, what it means is the vectors that constitute the support of w. So all the xi's are vectors, they are input vectors or input samples. The vectors that constitute the support for w are those for which lambda I is non-zero, and that's why we refer to them as support vectors. So it comes from
Yes,
there.
sir.
And
Sir,
if you take, for example, let's take an example like the AND gate. You have 4 samples here, right?
yes,
And here is your hyperplane, somewhere here like this. And if you notice, the samples closest to the hyperplane are the samples at this location here, 0, 1, 1, 0, and 1, 1. The sample at 0, 0 does not, influence this hyperplane at all, because it doesn't have anything to do with the margin here. Okay, and therefore, you will actually find that lambda I for this sample at the origin is actually 0. So the sample at 0, 0 is not a support vector, and the other 3 are support vectors.
yes, sir.
Yeah.
Yes, sure. Sir, last is that what's the hardware platform challenges for ANN implementation, SVM and MCM implementation? If you need to implement these algorithms on hardware platform, what will be the challenges?
So you can see even from the slide, if I want to implement, implement any of these models on, let's say, platforms such as smartphone or any other, what do you need to do? So the summation involves, let's say, doing a bunch. So let me write down what the discriminant function is. So the discriminant function f of x. So given a sample x, what do I compute? I compute w transpose x plus b. So if you copy w from here, you get something like, okay.
Yes. Sure.
And if you see this, the number of computations I have to do depends on how many of these lambda i's are non-zero. So you want a small number of support vectors, and that's essentially saying if I have a large data set, I want the lambda i's to be 0 for most of them. If you're able to do that, then one, you don't have to store all the xi's. You only need to store those for which the lambda I is non-zero. So storage goes down. If you have very few lambda i's which are non-zero, then the number of computations here, the number of multiplications is going to be the number of elements for which lambda I is non-zero. So that means the number of support vectors. So the smaller the number of support vectors, the less computation also you have to do. So it will be faster. So when implementing on, let's say, in hardware, what you need to worry about is that can you actually keep the number of support vectors as small as possible. This is one part of the overall, answer. The answer actually has three parts to it. I'm sorry,
Yes.
something was just moved. So I'll give you the other two parts. Okay. And
Yes, sir.
so what are the other
With
parts
this-
of it? Huh? Yeah. So if I take more, general, let's say a kernel version of this, so it will be W transpose phi x plus b, and this will be essentially 1 to m. This will be lambda I yi phi of xi transpose phi of x plus b, and because we use the kernel trick, sorry, this is oh. Yeah, sorry about that. I don't know. It's a little bit. This pen is a little glitchy. So let me see if I can fix this. So this will simplify to something like now here I have to compute a kernel function, and so the additional work I have to do is computing a nonlinear function of two vectors. So some cost of implementation can be reduced if you can use kernel functions that are simpler to compute, right? That require less work to implement or compute. The third part of this answer relates to precision. So if you're using floating point arithmetic in implementing it, then of course really there is not much to say. But a lot of the implementations really to save computation and also save power, they used fixed precision. So if now you start assuming that lambda I and k and b are all fixed precision numbers, not floating point numbers, then you're no longer really solving or using the original hyperplane. So imagine if I quantized these coefficients, what would be the effect? So there is some newer work that we'll probably we'll be able to see in a short while. As a PhD student of one of my PhD students, Mayank, who now has his degree, but he's done some nice work on this. That relates to what happens. Can we do something like, can we reduce the precision of implementation and still be able to achieve good generalization? And when is that possible? So if you look at fixed precision, it's a very difficult question, but it's possible actually in many situations. What we are able to do is we are actually able to we're actually able to do exactly that. We're able to obtain similar, or in fact sometimes better generalization in the presence of fixed precision. Okay, so that's essentially the summary of this last bit.
Hello, sir.
Yeah.
I'm Chandrajit Chaudhary. I have one question here.
Yeah.
Can we use your proposed method in a multi-class classification scenario by using one versus all or one versus one mode? So in that case, will it have the same? Can it have the same? Computational gain over the designing a network which will have the same. Which can itself have the multi-class capability.
Yeah, so it's a good question. There is some work in that respect. So it appears as if in neural networks, since you can just use all the classes at the output, you might imagine that the work of work doesn't actually increase with respect to number of classes, but that's not entirely true.
Okay.
So as you have overlapping classes and as you bring in more classes, you start to have interference between the maps and between the learning that's accomplished by the network for discriminating one class from another.
Okay.
So you can actually have, for example, I will give you some examples from the image processing domain.
Okay, sir.
If you have, say, several hundred classes, different types of images, categories, and so on.
Mm-hmm.
Many of the neurons at the output will turn on to some extent. And what you usually do is you do some kind of softmax or max function to
Yes.
obtain a probability of the input sample belonging to one class or another. So what tends to happen is that in many of these situations, your top 5 accuracy will be very high. So it's like saying that one of the top 5 neurons, which is the one with the highest probability neurons, one of the top 5 neurons is the correct class, and it might be as high as 98 or 99%. But if you ask me what's the top 1 accuracy, that means, if I just pick the neuron which is having the highest probability of firing, how often is that giving me the correct class? And that might be as low as 50 or 60%. So what that means is that you are really not discriminating between the right class and some other similar looking class. So the trouble with having some of these networks with very large number of classes is the disambiguation of classes that are similar might not be as finely done as possible.
Okay.
But that being said, that's not true with all architectures. There are ways to get around it. What I'm saying is, if you combine these methods with methods that reduce the model complexity, you will improve generalization across the board and you will get smaller models. Smaller models also means less confusion, so you're likely to actually get a second benefit. You'll have smaller models, it's easier to compute, faster to train or test with, and at the same time you get improved generalization. So it's not like one versus the other. You can actually use one in combination with the other.
Okay. Thank you, sir.
Sure.
Hello. Now I would like to request to Professor. Hello. Now I would like to request to Dr. Kash to kindly proceed further, because maximum there is some participant sites I have already passed on to Professor Jayadeva.
Okay, sir. Okay, sir. We the participant especially show our highest gratitude to you, sir, for being with us and sharing your valuable knowledge and experience with us. We would like to thank Professor Jayadeva, sir, for taking all the pain to deliver his wide range of research experience with us. We assure, sir, it has been a big learning experience for all of us, and all the participants must have benefited and noted down ideas for their future research work. Sir, we hope to get such opportunity in near future also, sir. Thank you, sir.
Thank you.
Now, dear all the participants, our next session will be resumed at 2:30 p.m. by industry expert Jai Mangal Singh, CEO, Redtron Education Service LLP, Bangalore. The topic is machine learning application in cardio diagnosis, and the YouTube link for the same you can find from the PDF that I have already sent to you. Thank you all.
Okay, thank you.